This is Roberto K6KM, and this talk is about portable antennas. A little bit about me. I retired from the semiconductor industry in 2016. I was an analog IC designer. Been a ham since 2018. I received my extra AJ60Y, and a year and a half later, I got K6KM. I enjoy contesting. I belong to the Northern California Contest Club. I enjoy DXing. I belong to the Northern California DX Club. I enjoy very much summits on the air, SOTA. I'm a 1.5 times mountain goat and 14 times shack sloth. When I go to a SOTA peak and happens to be on a POTA park, I upload my log, so I have POTA activations. I like building antennas, operating, and chasing those rare entities. More than 63,000 QSOs in the log under my call sign, and many more from multi activities. As of today, I have 362 SOTA activations, and DXEC is 302. Yes, I belong to all these clubs and probably more. And these are some pictures of my SOTA activations. This one in the Bay Area, Mount Allison. This is in Cordoba, Argentina, and this is in the state of Rio de Janeiro in Brazil. So what constitutes an antenna? What is an antenna? An antenna converts electrical signals into electromagnetic waves, or conversely, picks up electromagnetic waves and converts it to an electrical signal. To have an antenna, all you need is a conductor element, it could be aluminum, copper, anything that conducts electricity, and a means to effectively deliver power to that conductor. If you have that, you are guaranteed to radiate somewhere, somehow, in some amount. But that's an antenna. How about a good antenna? Well, if you talk to hams or you watch a lot of YouTubes, you kind of feel the theme of what hams usually define a good antenna. First, SWR 1.0000000 to 1. That will make a very good antenna. And also made a QSO with my next door neighbor. If they do those two things, Mr. Bearded Ham is very happy. But our little girl knows much better. Now, the bearded guy made the definition of a good antenna based on just two considerations. So I'll make my own definition of a good antenna also using just two considerations. So what is a good antenna? I will claim that the first parameter is efficiency. Antenna has to be efficient. What does that mean? Well, I put 100 watts into the antenna. 100 watts gets radiated in electromagnetic waves. That's 100% efficiency. If we go back to a typical horizontal center-fed dipole in resonance, we know that in resonance, the input impedance is purely resistive. That's the definition of resonance. There's no reactive component, no inductive, no capacitive. It's pure resistor. And the input resistance in the feed point is going to be composed of 3 resistors, one good one and 2 bad ones. The good one is called radiation resistance. That is what gets propagated. Now, why do we talk about a resistor here? Well, it's very difficult to measure how much power gets radiated from an antenna. So we model that power by a resistor that dissipates the same power in heat as the antenna radiates out of the conductors. The current is the same as going through this resistor than is as going to the antenna. So that's the good resistance, and we want the input resistance to be dominated by this radiation resistance. But we have current through conductors, so we're going to have ohmic losses. That's RL, but that's a parameter that is under our control. If it's too high, we can resort to go to a wider diameter conductor or use a better conductor that has higher conductivity. And the third resistor that is bad is losses to nearby objects. That could be a car parked next to the antenna, could be trees, could be the gutter when the wire is coming down next to the roof of our house, or most of all, earth or ground. The The ground can be a big sucker of power from an antenna. It's power that is not going to be radiated, but is absorbed by the ground. Two more inferences I'm going to make about antennas for efficiency. One is that you need at least 1/4 wavelength conductor to radiate efficiently. You can have a shorter conductor, albeit you're going to have lower efficiency, and the radiation resistance decreases quadratically with a linear decrease in conductor length. So if you shrink your conductor in half, your radiation resistance will decrease by a factor of 4. So it decreases dramatically. Let's give an example using our friend, the bearded ham. He goes to the store, he wants to do 40 meters DX. And he browses a bunch of antennas at the store, and he found one that is a 1/4 wavelength, base-loaded, short vertical, only 6 feet radiator, comes with 4 1/4 wavelength radials, and is pretty cheap. So he decides to order that one. The salesperson tells him that he better put it about 20 feet up. He says, okay, goes to the house, looks at his backyard, goes to Home Depot and buys 2 10-foot electrical conduits, put them together, and makes a 20-foot pole, puts the radiator on top, puts the 4 radials strung horizontally, and he connects his antenna analyzer. He looks at it, and oh boy, he finds that the feed point impedance is 1/2 ohm, and the SWR is 96:1. So he gets frustrated and decides that this antenna is no good. So he takes it all the way to the ground. In the process, he forgets to take the antenna analyzer out of the feed point. So he looks at the antenna analyzer, and holy macaroni, his feed point impedance is 36 ohms. His SWR is 1.321. He is a happy camper. Well, little girl knows better. What just happened here? Well, when the antenna was up in the air, 20 feet, which is what our salesperson told us, is because the input resistance was dominated just by the radiation resistance and the ohmic resistance. There was no much in terms of losses to ground. When he lowered the antenna to ground, now what happened? Well, the radiation resistance is still the same because the radiator is still 6 feet. The losses are still the same because he's still putting the same power to the antenna. But now he brought in this ground resistance, his losses to ground. And they're huge because he only has 4 radials sticking down to the ground. The radials are not even going to be, they don't need to be 1/4 wave anymore because they get totally detuned by the ground. So basically what he has is a 35.5 RG against a 0.5 RR plus RL. So his efficiency is going to be pretty much 0.5 divided by 36. That's pretty low. Now let's look at 0.5. Is 0.5 real? Well, remember, a 1/4 wavelength, 40 meters, is 34 feet approximately. And he bought a 6-foot radiator. So he shrank 34 feet to 6 feet, and we said it's quadratic. So that's totally plausible. 1/2 ohm. Very low radiation resistance. Now, you're going to say, how do you provide power to this thing since SWR is 96.1? Well, that's not a big problem. We know we can use impedance transformation with transformers, we can use tuners, we can use other means of coupling impedances. What is important here, the point here, is that you want an efficient antenna. The 20 feet up antenna is tons of times more efficient than this other antenna on the ground, even though the SWR is almost 1:1. That's the point. Now, the next consideration for a good antenna, and the last one, is that the propagation directions of electromagnetic waves match the desired outcome. What does that mean? Well, If I want to make contacts with Europe, I'm going to try to get all my propagation into the direction of Europe. If I want to work Japan, I want to make sure all my propagation goes towards Japan. If I'm in a contest and I have to contact anybody anywhere, I might want to have omnidirectional an omnidirectional antenna because I don't know where my customers are coming from. So our friend, the bearded ham, he goes back to the store, returns the quarter wave, and starts browsing another 40-meter antenna to the DX. Many friends of him told him just put a dipole. And so he looks at the 40-meter dipoles. They're cheap. It's just a wire. So he buys one. The salesperson tells him, oh, you're going to do DX? You better put it 66 feet high. That's a half a wavelength. Well, he goes home. He looks up at his backyard. There are no trees. He's not going to buy a tower. And after a while, he says, well, why do I need to put it half wavelength up? Well, because you want to have this type of radiation pattern. You want to have a very low angle takeoff and lots of gain towards the horizon. That's where your DX is going to come from. Not only that, but you don't have much energy going up. So you're not going to be picking up strong stations nearby that are going to clobber the DX that you want to hear. So that's what you really want. Okay, but I don't have 66 feet. So I'm just going to put it on the fascia of my roof. It's 15 feet up, and that's all I can do. He does that, and his radiation pattern looks like this. This is what is called NVIS, Near Vertical Incidence Skywave. So when you put a horizontal dipole too close to the ground, well, the energy is going to bounce back to the sky, which is wasted energy in many cases. But there's going to be a bunch of power also going into high angles. And what's going to happen during the day, there's no propagation on 40 meters, long distance propagation. So anybody that does SOTA or POTA, 40 meters is actually a pretty good band. The signals that come back are pretty strong, and you can work lots of neighbors. How does that happen? Well, through the near vertical incidence skywave. You shoot the energy up, diffracts in the ionosphere, comes back down in a very high angle, and you contact your neighbors. That's okay, but that's not what he wanted. He wanted DX. Are you going to have DX with this antenna? Well, you could, because you still have some low angle. The only problem is 25 dB lower than what he was getting here in terms of gain. So our friend Ham decides to call CQDX anyways. He starts calling CQDX, and after 5 minutes, there's this station in the Canary Islands. It's a contesting station, has monoband towers with stacks, and they happen to have a stack of 3 40-meter Yagi, three elements each. They're in a very quiet location in the island. They're next to salt water. And the operator there hears this faint signal out of our friend the Ham. So they go back and they send their signal with 1.5 kW minimum. And our friend hears the signal. He makes the QSO. He is happy. He made a DX QSO. Why did they tell me to put it 66 feet high? I have it 15. I just made a QSO with the Canary Islands. So he's happy. After that, he keeps calling CQDX for about 3.5 hours, doesn't get any single QSO DX, and he resorts to go to FT8 and work the East Coast. So our little girl knows better. Portable antennas. Since I'm the one presenting, I have the privilege of creating my own distinction about portable antennas, and I will divide it in 3 different categories. The first one is luxury portable, as can be seen in the picture. Second one is POTA portable, very convenient with a picnic table. And SOTA backpacking portable, usually super light because you have to bring everything with you. Luxury portable. This is Tom, an S60, and myself at the California CUSO party, getting the first place expedition category on Tulare County. How did we do that? Well, normally on an expedition category, you would think that people will go to a ridge, bring generators with them, big tents, spend the night in the cold, wire antennas. Well, we were at the US Tower factory in Woodlake, California, and they provide us with exceptional facilities, air conditioning, kitchen, and not one, but two 120-foot tilted telescopic portable towers. We use one that we keep about 50 feet up with a tri-bander, and the second one we put an 80-meter dipole on top at 125 feet, and we can string also a 40-meter inverted V dipole at 66 feet. So that was really nice. Now, that's luxury. You don't have to go to that extreme, but our friends at Palo Alto Amateur Radio Association, they come to Pacificon every year with a trailer, a little rusted. Probably they got it pretty cheap, and a decent telescopic tower, and they can actually have pretty big Yagi on top, and is enough for me to call it luxury. So I'm not going to talk about this category anymore. This is all I'm going to say about it. I don't think you want to show up on a park doing POTA with one of these portable towers. For POTA is really convenient. You can operate from your vehicle. You can actually have your antenna attached to the vehicle. Seldom backpacking is involved. I have done some POTA backpacking just because I wanted to, and I climbed some hills. And then when I was at the top, I had a nice ridge with a fall to the right direction, and I could leverage that to get some gain in the direction I wanted. And I operated QRP. But usually people operate on a nice picnic table. They might or might not need to be stealth, even though one of the problems with POTA and sometimes SOTA too is wires on the ground and dogs, they don't mix very well. So you have to be careful, and you have to know your surroundings. You don't want to call for attention either, because you don't want the park ranger to come over and see what you're doing. Usually the operators operate 100 watts because they can bring bigger rigs and bigger batteries. 100 watts SSB. Many do FFT these days, and some do QRP, CW, or 100 watts. But the main thing is that your antennas can be rigid antennas because you're bringing them with your car. So you can spend a little bit of time mounting your antennas and enjoy some game. SOTA backpack portable. Well, you have to carry your antenna, your radio, your battery, your water, everything with you. So the equipment has to be super light. You also want a quick setup because after you hike for an hour or two, you just want to operate. So you want to set up your station very quickly. Usually you operate CW, QRP because of the weight, and CW because it's very efficient. You might need to be sometimes stealth because you might operate on very touristic peaks. Here, W6PW is at Mount Davidson in San Francisco, and it's usually full of people. So if you call too much for attention, they're going to interrupt you in the middle of a pileup, and that's not so nice. So convenience is the name of the game. On the right is me at Coyote Peak, operating QRP on a CWT from CW Academy. You don't want to be this guy when you are at the peak or at the park. You don't want to be tangling wires. You don't want to have complicated setup. So you want to be simple. The most efficient you can be. You want to be light. Easy to use. You don't want to have to start opening manuals to learn how to use something on your rig. You want to be multi-band if possible because there might be an activator on another park, on another peak, on a different band, and you want to have that band available. Band or possibly also mode. You want to set up to be sturdy. And in some places it's very windy. Sometimes there are bikers passing by and they might not see your antenna. You want to be fast deploying and fast taking it down. Why? Well, the weather changes very quickly on peaks. Convenience, again, is the name of the game, so we will focus only on SOTA and POTA antennas, no luxury. We start usually with a classical horizontal dipole. For POTA, which means not backpacking, you can bring something rigid, and usually people resort to something like a body pole. That's kind of a shortened horizontal dipole because they use inductors in the radiator, not necessarily at the feed point, a little off center, and makes your antenna look longer with the inductors, but your bandwidth might be lower. You can see that the height is not that great, and that's because the tripod, so much it can do. Also, you have to guide it if it's a windy place. So it's gonna be kind of envious, but you're gonna be able to operate and get your contacts. You can also homebrew a horizontal dipole. You can buy yourself some 17-foot telescopic whips, usually made out of stainless steel for mechanics. They're gonna droop because of the weight. Height is still a problem. It's hard to get something multi-band. You can change bands, but you have to lower the mast, change the size of the telescopic whips, bring it back up, and off you go. Now, stainless steel is not a good radiating element. Usually is 20 times less conductive than copper. But in many cases, your RL, your ohmic losses, are not your main problem. Most of the time, your main problem are ground losses. So you can probably live with that. Horizontal dipole on a SOTA environment. Well, in SOTA will have to be a wire antenna. And, 40 meters, 66 foot long is a long wire. You need 2 trees to set this thing up, or 2 poles to set it up. If it's 2 trees, well, it might be a miracle that when you get to the peak, you actually have 2 trees that are farther apart or close enough that you can actually string something like this. Or if it's 2 poles, well, you have to carry 2 poles. And I will argue that you might need a 3rd pole because your center point will need a balloon, a choke, and that is going to pull down because it's heavy. And also your feed line that is coming down is going to pull down. 33 feet of feed line of coax weighs quite a bit. So you might need a 3rd pole. That is too much. And usually people who try this, they tried it one time and then they look for something else. Let's look at what the radiation pattern for a 40-meter dipole center fed at half wavelength up 20 meters is going to look like. First, we look at the impedance, and it's about 75.67 ohms, SWR 1.52, that's okay. The azimuthal pattern is the typical donut shape, that's okay. And your vertical propagation is low angle, and you have some gain, not too high, about a 30-degree angle or so. So that's usually what you're looking for when you want to do DX. There's not much energy wasted going up. And yeah, it's fine, except who has 66 feet of pole in the field? Well, let's see what happens when we lower the antenna to 1/4 wavelength. That's a height of 10 meters, 33 feet. That's a standard size for a fishing pole, so that's not a big problem. And we get an SWR 1.6, the impedance about 80 ohms, is a little higher because you're closer to ground. The azimuthal pattern is still a donut shape. The vertical has a takeoff angle, but it's the classical NVIS, right? Most of the power goes all the way up. So yeah, that's practical for SOTA and POTA, but it's not a great DX antenna. Well, let's be ambitious. What happens if we put it one wavelength up? Let's go up. We don't have 66, but maybe we can have 120 feet. Well, let's be ambitious and let's see what happens if we put the antenna even higher. If we put it one wavelength height, 40 meters, 120 feet plus. Well, the input impedance is about 80 ohms. The SWR is 1.52. The azimuthal is still a donut shape. But here, I get two lobes. What do I get two lobes? Well, the antenna is 2 half wavelength up. So that's going to change the way my vertical radiation pattern behaves. Is that all bad? Well, not necessarily, because actually now I have a lower takeoff angle. I might not have as much gain because now I put a bunch of that gain, a bunch of that power much higher up, but I have a nice takeoff angle. And but who has 120 feet up, right? Well, it happens that if you are in New Mexico or Arizona, when the mountains are mostly a big rock or a big pile of rocks, rocks are not very good conductors, right? They are very lossy. And when the antenna is up there, it might not see the ground as a good ground. So it might actually think that it's sitting up in the sky with nothing underneath. I wanted to find a nearby example of what such a mountain here in the Northern California. It's very hard because mountains are like that, but there is one, Fremont Peak. It's 3,173 feet, and the peak looks like this. And the top is where the flagpole is, which is where we usually activate SOTA. And then there is about 50 feet or 70 feet of rock, and that continues underneath. So you could say that somehow, if you are here at the top, that might happen. And what happens is you are 967 meters up for a 40-meter wavelength. You're 24.2 wavelength high. Well, your impedance is 73.48, which is starting to get closer to impedance of a halfway dipole in free space. SWR 1.47, azimuthal is still a donut shape, but look at our vertical pattern. It's full of lobes, and there is quite a bit of power going all the way vertically to the sky, which is not good. Now, we're still going to activate here because many people are not aware of this. And what happens when you do this is, let's say I'm in California and I'm talking to a station in Colorado. The station in Colorado is sending the signal. The signal goes up to the ionosphere. It refracts back to California, and I'm picking up with this angle. And it happens to be at the peak of this lobe. So I'm hearing the station very well. Well, the ionosphere is not a very thin layer. It's a relatively thick layer, and also is constantly changing in terms of density, in terms of where it's located, in terms of how thick it is. So the point of diffraction is all the time moving up and down, which means my angle of incidence here is going to start changing all the time, and even more if there are disturbances in the ionosphere. So the signal is going to start traversing through one of these nulls eventually, and maybe going up to the second lobe and picking up signal here, and then maybe coming back to the null and then going back up to the other peak. That will manifest itself as QSB, as fading. and we think that fading is just something related to the propagation. In this case, might be related to the way your vertical propagation pattern looks when you're so high. Is that a problem? Well, you live with it. The problem is if you actually are trying to contact a station that happens to come at this angle and the ionosphere is pretty stable. You might never hear it, or it might be way, way too faint. You're almost at minus 18 dB gain in there. So, okay, we said the center-fed dipole, not very practical, too many supports, too much weight, blah, blah, blah. Well, how about an inverted V dipole? An inverted V dipole only needs one support. That's really nice. That could be a tree branch or could be one of the fishing poles. That's perfect. So we come down about 45 degrees on each side. We have an end insulator, a rope. We stake it to the ground. We put the balloon choke and we come down with the coax, but now the support is helping us. Yeah, our horizontal azimuthal pattern is not so much a donut anymore. It's a little more omni, not quite, but more. That's not a problem. And our vertical now has a little bit more energy on the top. So I lost a little bit of that angle to power going all the way up, but it looks very similar. The SWR is beautiful. We'll put our bearded ham really happy. 1.039 with an impedance or resistance of 48.14 ohms. So this is a very valuable solution. Inverted V is the way to go. But I want to have more bands. So how can I do that? Well, suppose you have a 80-meter dipole inverted V, and if I cut the wire to 20 meters, 30 meters, 40 meters, and then full length 80 meters, I can put links. Links are nothing but connectors. In this case, for instance, alligator clips, and the acrylic here is just holding the wire together. I can connect or disconnect these links and make 20, 30, 40, or 80 meter dipole inverted V. I can use also banana jacks, whatever that connects and disconnects. And the only problem is every time I want to change band, I have to get off my chair, go there, lower the mast, connect and disconnect the links, lift up the mast, then go back to my chair and start operating. And that's quite a little bit of time and inconvenience. Another way of doing this is using a trapped dipole. What are traps? Traps are just LC parallel circuits. So you have an inductor and a capacitor. And when this circuit resonates, the reactive part of the inductor cancels the reactive part of the capacitor. So you end up with whatever resistance is left, which hopefully is very little. So it's pretty much an open circuit. So if we put a 20-meter trap at the right distance and a 40-meter trap at the right distance, when I apply a 20-meter signal in here, the trap is going to be resonant, so it's an open circuit. So I'm only going to see this part of the wire. The signal is not going to be able to go through. If I put a 40-meter signal, 7 megahertz, then the signal is going to go through the 20-meter trap all the way to the 40-meter trap that is resonant, and it's going to look like an open circuit. So this is great because I don't have to get up my chair and start changing bands and changing clips and things like that. However, one thing that happens is when I go through a trap that is not resonant, for instance, a 20-meter trap on 40-meter signal, that trap is going to look inductive. And we know what happens when we put an inductor on a wire. It makes it look longer. So that's not so bad because actually I can cut some of my wire for 40 meters, which means my antenna is going to be a little shorter than what it was originally. And that's very practical in the field. Makes it tuning a little bit more tricky, but it's totally doable. And you can put as many traps as you manage. Now this is for QRP. Uh, there are traps for 100 watts, but they're not very practical in the field. They're heavy. The voltages at resonance are very high, so the capacitor in the trap is actually a high voltage capacitor. This one QRP is rated 500 volts. When you go to 100 watts, it's going to be rated in kilovolts. So yeah, the trap dipole is actually very practical, particularly for small rigs that have limited number of bands, like the mountain topper. 3 bands is 20, 30, 40. So you just put two traps and let the dipole go all the way to 40, and you're set. You don't have to get off your chair. Now let's look again at the center-fed dipole and how it behaves with harmonics. The fundamental is the solid line, and we see that there is low current at the edge because there's no place for the current to go. It's high current at the feed point, and it's low current at the other side on the edge. So high current, low voltage, low impedance at the feed point, very easy to match to a 50 ohm load. The second harmonic is the dotted line, this one here. And we have low current at the edge again, we have low current at the feed point, and we have low current at the other edge. Low current at the feed point means high voltage, that's a high impedance node. It cannot be excited with the setup we have. So the third harmonic is this dashed line. The red one is low current at the edge, high current at the feed point, low current at the edge. So I have high current, low voltage. Again, I have a low impedance, easy to match. So third harmonic is okay. Fourth harmonic is the solid line. It's low current at the edge. It's low current at the feed point, low current at the other edge. So low current, high voltage, high impedance. I will not be able to excite this harmonic with the setup we have. Fifth harmonic is the short dash line. I have low current at the edge, high current at the feed point, low current at the edge, high current, low voltage, low impedance. Fifth harmonic is okay. And you can see the trend. So what happens? I can actually excite a center-fed dipole with third harmonics. So in the example, I had a 40-meter center-fed dipole. I can also get a 15-meter band. That's nice. I gain 1 band, but I want more. So let's look at a dipole and all the harmonics and see how we can excite the dipole in all the harmonics. To do that, I will have to find a place where the current is pretty much the same, meaning the impedance will be pretty much the same no matter what harmonics I have. There are 2 points in this dipole when that happens. Yes, the edges. That's low current, high voltage. If I excite my dipole through the edge, I can get any harmonic I want. So if I have a 40-meter dipole, and if I feed it at the end, I call it end-fed half-wave dipole, I can get 40, 20, 15, and 10. That's nice, but how do I go about exciting a dipole through the edge? A dipole can be excited anywhere. We usually excite it in the middle because we have a symmetric structure. It's much nicer and it's low impedance, 72 ohms in free space. That's close to 50. It's easy to match. But there is impedance on the line all the way from 72 to about 2500 ohms at the edge. Anywhere in between, it has some impedance in between. But in this case, we want to feed it from the edge, from the end, 2500 ohms, because we want to get all those even and odd harmonics. So how do we do that? First, let's start with an inverted V. Inverted V, I want to feed it at the edge, 2500 ohms. How can I bring it back to 50? Well, it might be a little too much for a tuner, but we can put an impedance transformer. We know that if we have a voltage transformer, the voltage transformer is nothing more than the ratio of the turns, primary and secondary. The impedance is the square of that turns ratio. So if I have a 7-to-1 or 14-to-2 or 21-to-3, I have a voltage or a turns ratio of 7-to-1. If I square that, I get 49-to-1. So I can make a 49-to-1 transformer and get the 2500 ohms close to 50. And that's what we do. Now, the transformer has two wires because we come from a feed line that has two wires, the center connector of the coax and the shield. Where does the other wire go to? Well, you need a return. You need another part of the antenna. The antenna always has these two parts. After all, it's a dipole. So we put a little piece of wire that we call counterpoise or counter antenna. How long it will have to be? Well, it depends. It depends on what band it is. It depends how close to the ground it is. Depends on a lot of stuff. So we just put some wire in there and hope that it's going to work okay. And then this antenna is very non-symmetrical, right? I have 66 feet of wire here as inverted V, and I have maybe a 13 feet, 17 feet piece of wire as a counterpoise. So it's very non-symmetrical. And so currents, I will try to come back as common mode through the feed line. And that's not good. That's not good because the current is going to come back all the way to the transceiver and you can get RF burns. If you have a computer connected to it, you might start getting problems with USB, locking up the computer. So you want something to stop those common mode currents in here. And we do that by putting a common mode choke. And that way we stop all those common mode currents from going through the feed line. How does it do that? Well, there's a ferrite, there's a bunch of turns, and you're hoping that the resonance of that choke is going to be on the band of interest. And when it's in resonance with the parasitic capacitance of turn to turn, the core is going to start dissipating. The core is on purpose is going to be very lossy. So it's going to start dissipating and it will dissipate all those common mode currents as heat. And that's what you want. So you stop the current here. That works pretty well. Now there are people that choose to use the external part of the shield where that common mode is going as a counterpoise. So I don't have to use this other wire. Of course, then the feed line will have to be a certain length, and they recommend 20, 25 feet. But you still have to put the choke. This time, you put it at the entrance of the tuner or the rig, because you still don't want those currents to come back and bite you. There are different configurations. You can also do sloping, because after all, the high currents on the harmonics are in different places. But the problem is with a 40 meter, 66-foot wire, this is going to start drooping quite a bit and it's going to start getting too close to the ground. So this is used sometimes, but it's definitely going to be lower performance than an inverted V. You can do also inverted Ls. You can do random shapes. In practice, this 49-to-1 is not only doing the impedance transformation, but it works as a anon. We go from unbalanced, the antenna is highly unbalanced, to unbalanced, our coax is unbalanced. So it's an anon, has impedance transformation of about 49-to-1. And it's built usually around a core. You can build it yourself, it's not very difficult. The size of the core will depend on how much power you're applying to your antenna. And you can buy it commercially. LDG makes them and some other companies make them too. For QRP and for 100 watts, Atom K6ARK makes really awesome kits that you can purchase. And you end up with this little BNC connector with the Onan built in, and you just go straight to your antenna. You don't even need a feed line. So it's pretty awesome stuff. Now let's look at what happens to the radiation patterns on all these harmonics. We know we have 40 meters on a center-fed dipole. We can get 15 meters, that's great, but where is the power going to? So at 40 meters, half wavelength up, we get the typical nice low angle power going to a relatively low angle. So we have seen this before. Now we go to the third harmonic, 15 meters, and what happens? Now the antenna is a little too high in terms of half wave lambdas, half wavelengths, and we start getting repeated patterns, and they interact with each other, and we end up with this multi-lobe type of pattern. Is that all bad? Well, not necessarily. Look, the low angle is really low, and there is a big gain point at very low angles. So it should work fairly nice on DX. It should work okay with closer stations. Now it has a big null here, so if a station is calling you and is coming on this angle, you're going to have about 16, 17 dB low. So you're going to struggle to hear that station. And then there is quite a bit of power just going to the sky for no reason. But you still get 15 meters, so that's not too bad. What happens to an NFET where you can get all even and odd harmonics? Well, 14 meters is exactly the same because it doesn't matter where you feed your dipole, it's still a dipole. So you get exactly the same elevation pattern. Second harmonic, well, again, you get two lobes, low angle, you get gain, not too bad. 15 meters should look pretty much the same as the previous one, and it does. And in 10 meters, you start getting more lobes because you are too high for a half wavelength. And you get this nasty up to the sky power lobes that are not so good, but it still works at 10, not as good as you would like it, but you get 10 meters, so it's convenient. Now we want more bands. We don't get the work bands. Where are the work bands? 12, 17, 30 meters. Well, it turns out that if you slide the feed point away from the center and you find a place where you can actually get somehow a 3-to-1 SWR in all the bands of interest or most of the bands of interest, you could feed it over there, and this is what's showing here, and you can get 10, 12, 15, 17, 20, not quite 30 meters, but you get 40, which is the fundamental of the dipole. And if you have a tuner, just 3-to-1, typical tuner from a rig, you can bring your SWR back to happiness, 1-to-1. So you can get more bands. It's still an unbalanced antenna. The impedance is not 50 ohms, so you need some type of matching, in this case 4-to-1. You need a common mode choke because it's going to be very unbalanced. You don't want currents coming back through your feed line. And where do you place the feed point? Well, that's debatable. People have done a lot of tests. They recommend one thing or the other. In practice, it will depend on your configuration. Where it is anywhere between 1/3, 2/3 to like here, about 18%, 82%. And you'll have to play with it. And we come to my favorite antenna in the field, the NFET random antenna. Is it the most efficient? No. Does it give you the best radiation pattern? Probably not. But oh boy, it's convenient, and you'll see why. So the idea, by not being so random, is that you want to resonate in a frequency that is away from any ham band. So you do have to be at least 1/4 wavelength on the lowest band of interest, but you don't have to be half wavelength as an NFET half wave. So it's going to be a shorter wire. And if you look at the SWR pattern, it's going to resonate somewhere, and it's going to give you SWR less than 10-to-1 in all the ham bands, from the place where you get 1/4 lambda above to the highest band you can achieve. Now, yes, you do need a tuner, and a very good one. Most of rigs who have 3-to-1 type of tuners won't do it. My KX2 picture here has a very good internal tuner. It can easily do 10 to 1. If your rig has 3 to 1, you can buy an external tuner and that is capable and can do 10 to 1. They're not too expensive these days. Now the antenna, a piece of wire, in my case 41 feet, you do need a counterpoise. I use 30 feet. This antenna is highly non-symmetrical, so you'll need a choke at the feed point, and you'll need a transformer because your impedance at this point is something, and usually is for this type of length in the order of 450 ohms, so a 9 to 1 transformer, impedance transformation, will do. They tend to be very efficient, those transformers for QRP. At 100 watt type of power, those transformers are still quite efficient in the 85 to 95% efficiency. So it's not too bad. Now, why do I like this so much? Well, I'm sitting here on my little chair and I'm working somebody, in this case on 15 meters, and I see that another activator is in a mountain on 20 meters and I want to make a contact with it. So what do? I just change the frequency to where he is. I punch the tuner, gives me 1 to 1, and I'm ready to go. So it takes me less than a second to actually change bands. And I can change all the bands from the lowest one to the highest one I can achieve with my wire. In my case, I can do 40, 30, 20, 15, 17, 12, 10, and even 6 meters. So it's extremely convenient, and that's the name of the game. Another thing is your wire doesn't have to be inverted V because you don't know where your high current point is going to be, and that's why efficiency might not be so good, and radiation pattern might be whatever. So, but you still get to have pretty good activations with it. It's very, very convenient. Now, if you want to have very small real estate, you start thinking about going vertical, right? Well, not so quickly because you need a good field of radials to make the vertical efficient. And the number of radials affects your efficiency. To be efficient, you probably need in the order of 32, 64 radials. I don't think anybody wants to go to a peak and start laying out 64 radials, even in a POTA park. And besides, as I said before, dogs and wires don't mix very well. So it's a hassle. If you only put 4 radials, your efficiency is going to be very low, and especially if your radiator is low. And remember the beginning of our presentation with the bearded ham. So a feed point impedance for a quarter wave vertical full size should be 36 ohms. Is half of a dipole, right? The other half is the image mirror on the other side. As you saw before, if you put it on the ground, you can fool yourself by measuring a nice 50 ohm feed point impedance, and that all it means is ground losses. Not only that, but your antenna is going to have a great bandwidth. What's the best bandwidth you can have? A dummy load 50 ohms, right? So the ground also detunes the radials, so they don't need to be a quarter wave. But if you put this close to salt water, it's a different story. This low angle that you get on a quarter wave vertical actually gets all the way down here, and this high gain point lowers to very, very low angles and is a winner. And that's what most of the expeditions on Pacific Islands use. So this is really cumbersome to deploy SOTA and too time consuming for POTA unless you're willing to live with that low efficiency. But what if we elevate the feed point? If we do that, we might get away with fewer but tuned quarter wave radials. One way to avoid losses and make the vertical antenna a little bit better is to elevate the feed point. This has been studied quite a bit by Rudy Severs and 6LF, and we're lucky to have him here in the Bay Area. And so the feed point is the critical one because it has most of the current. See, if you elevate it at least 4 feet, better 5 or 6, Now you have less interaction with the ground. Also, the ideal thing will be to have the radios, which can be a lot fewer than the 3264 we're talking about on the ground. You can get away with maybe 4. Ideally, you would put them horizontally, and they have to be tuned, so they have to be quarter wave. But if you drop them all the way to the ground, better to avoid touching the ground, maybe keeping it a foot or 2 above the ground. That way, now your radios are resonant, so you have to cut them for the frequency. And this picture shows a 20-meter quarter wave vertical antenna, 17-foot radiator telescopic, and 4 radios cut to quarter wave. Of course, this is more of a POTA setup than a SOTA setup because you're going to need a very sturdy tripod. You can do also anything from 10 to 20, 10, 12, 15, 17, 20, but you have to cut the radios for those frequencies, which is a little painful when you're in the field, either wrap them on itself from the tip to the right quarter wave, or put one set of radios per band, which means now a lot more radios. And the SWR, you're going to find that will depend a lot on the ground type, the type of soil, and your surroundings. So you might spend some time tuning this antenna in one place, take it to another park, and you're going to see that it changed a little bit, but not dramatically, so you can use the tuner just to compensate for that. Nice power efficiency, omnidirectional in the azimuth side, and very low angle as you would expect. So this is a nice DX antenna if you're willing to live with one band. Now, vertical dipole would be really nice because look, Mom, no radios. So this is really compact. This is a stick up and another piece of wire coming down with the same quarter wave length. So if we take a horizontal dipole, center fed, and we rotate it 90 degrees, what happens is your azimuth now will be omnidirectional, which is not a bad thing, especially if you are doing POTA or SOTA. You don't know where your customers are. There's no need of radios, as I said, but it's non-symmetrical antenna. One side of the antenna is closer to ground, the other side is farther away from the ground. So you will need to have a choke at the feed line. And another restriction would be that your feed line better be 90 degrees coming out of your antenna, or that feed line will be part of the antenna. In practice, that's very difficult to do, particularly on the field. So you do the best you can, and you can see here is just drooping down. That will change a little bit the radiation pattern, but not significantly in this case. So let's look at the elevation pattern. Very low angle. You have a nice gain. Then you have some other lobe there superimposed. Not quite what you would expect with just a single lobe. And depending on how high or high-low is to the ground, this is going to change dramatically. Your feed point impedance is 72 ohms, SWR 144. If you look at this elevation study, because the big question is how high you have to have this vertical dipole, or particularly this feed point to the ground, to make it efficient and to have the pattern that you want. Well, if you look at this graph here, this graph represents the radiation efficiency in pink, the gain in blue, and the SWR in orange. And this here is feed point over ground in wavelength. The SWR looks very constant, which makes sense. So that's something that you don't have to worry too much about. Now the efficiency, if you are below one wavelength up, starts coming down dramatically. And the gain is also coming down dramatically. So this antenna is better when you can keep the feed point at least one wavelength up. In my case, I had a 10-meter vertical, and I put it at 15 feet. That's half wavelength up. With half wavelength up, my efficiency is about 40%. My gain is about 1.5 dB. So it's not what I would like it to be. One wavelength up will be 33 feet up, and then you need a guided structure, which is not that practical doing POTA. So it's good, but it has its problems. Now let's go to a real DX machine. All wire. This one was inspired for the lower bands, but it can be used on anything, even 70 centimeters. Again, Rudy Severns, N6LF, he's your guy. He has done studies on a lot of different antennas, and theoretical and practical. So this is the half square. The motivation is this. Let's assume you have a 40-meter dipole, horizontal, center fed, it's up on the field. So you have to put it, remember, half a wavelength up to have a low radiation angle. But that's too high. So the idea is, can I lower it to 1/4? Well, if you lower it to 1/4 wavelength, we have seen it before, you get this ENVIS type of pattern, and that's not what you want because you want a DX antenna. Okay. Let's assume I can add a 1/4 wavelength of wire coming down on one edge, and another 1/4 wave length of conductor coming down on the other side. Now I have a horizontal half a wavelength wire, one vertical 1/4 on one side, one vertical 1/4 on the other side, is sitting 1/4 wavelength up. Let me ask to put the whole structure up about 5 feet so it doesn't touch the ground. So it's 1/4 wave plus 5 feet. And as you can see, the end of the wire usually has the low current, high voltage, high impedance, because there's no place for the current to go to. You go 1/4 wave, you convert that into high current, low voltage, low impedance point. Now the 1/4 wave, low current, 1/4 wave, high current, 1/4 wave, low current. So if I cut the wire here, where I have high current, low voltage, I should be able to feed this whole structure with about 50 ohms or so of impedance. So it's very easy to feed this antenna from here. Okay, so let's feed it from there, this corner. What happens then? Well, what happens is I have a 1/4 wave vertical at the frequency of interest. I have a transmission line here of half a wavelength, which is doing no radiation. The current is coming down to 0 and then coming back up. And then this node is exactly the same as this one, is a replica. So this one will be feeding this vertical 1/4 wave. So what I end up with is 2 1/4 wave verticals at the frequency of interest that are separated by half lambda. So they're in phase. And what happens is then the radiation patterns add each other, and I get gain out of this thing. How much? We'll see pretty soon. And since they are verticals, I'm going to have a low angle, a low takeoff angle, and some gain in the lower angles. So this is the ultimate DX machine. It's not too high. It's easy to feed from a corner with 50 ohms, no radials, and I can have low angle and gain. In fact, if I put this antenna, well, we're going to see what happens with the ground, right? So this is an average ground. I get low angle, but my gain is lower because the ground is interacting. See, if I have a very good ground, there is less interaction with the ground, and now I have even lower angles and more gain. If I can put it close to salt water, I have a really low takeoff angle and a lot of gain on a very low angle. So this is used also in the expeditions when you're on the Pacific Islands and you want to have gain and a very low angle so you can work Europe, Africa, anywhere in the world. Of course, this is directional, so you will have to rotate this structure somehow depending on the time of the day, the place you want to work. Now, feeding from a corner is not so easy, so you could feed it from the end. The only thing is here, the impedance will be about 5,000 ohms. And you can still make a transformer at a feeding from here. You will need a counterpoise or radials, but it will be much easier to feed. If you can put it close to salt water, the directivity can be as high as 11 dBi. So can you use it in other harmonics? You can, but the pattern will be totally different. It won't be this DX machine anymore. You will end up with an omnidirectional pattern in 20 meters in this case, and some weird type of elevation angle pattern. Now let's talk about really convenient antennas. There's no such thing as free lunch, right? This guy is offering free lunch, but the plate costs $10. So convenience sometimes outweighs perfection. We saw already that on the random length antenna, right? These are extremely short antennas. This on the left is the Elecraft KH1 introduced last year. It's a CW only, a few bands, very portable. You can actually put it in the back pocket of your pants. Has a 4-foot radiator. Inside there is a loading coil, and it has a 5-to-1 tuner, very capable inside. What is the main thing of this whole setup? You can get on the air in under 60 seconds, so it's extremely convenient. Now, it does rely on an internal tuner. In fact, anything around the antenna will interact with the antenna. Your hands, your body. Wayne, the guy from Elecraft who actually designed it, he likes to say that the impedance will actually be affected by the operator's shoe size, which is true. Everything around it will affect the impedance, but you have the tuner, and you can tune even in the middle of your operation if you need to. It's a very short antenna, so it's very compromised. Works better near salt water. No wonder this picture is taken next to salt water. Works better on quiet summits because now your short whip antenna will be able to hear those faint signals that it's picking up. Works better when on top of solar cycle. I think it's no coincidence that it was released last year at the top of the solar cycle. It's extremely popular with people because it's a very, very convenient setup, 60 seconds or less. I have created a similar setup, not as compact, with my KX2 and a homebrew loading coil for 10 to 20 and everything in between, and a 6-foot radiator. Now, 6 foot is better than 4 feet, and we know that the increase in radiation resistance is quadratic with the linear increase of the radiator length. So my antenna, I expect it to be much more efficient than Elecraft's in this case. Another antenna that is very popular is the MagLoop. It's very small footprint, no radials. You don't have to put it up high from the ground. It does interact very little with the ground if you keep it up at least 1 diameter. This one works totally different than all the other antennas we saw. All the other antennas we saw, they create an electric field and they get the magnetic field for free. This one creates a magnetic field, thus MagLoop, and they get the electric field for free. Now, how does it do that? Well, the radiator has to be really small, less than 1/8 of a wavelength. But then we make it resonate with a variable capacitor that is sitting on this box. And then we can tune, using the variable capacitor, this LC network to the frequency we want to listen to. So we first select the frequency on the rig, then we tune this loop for that frequency, and in the field, one way of doing it is just listening for maximum noise. Then we can use the tuner on the rig just to give it the last bit of matching. And that's usually not a problem for POTA and SOTA, because in POTA and SOTA, we run the frequency. So we choose the frequency we want to run. We tune the magnetic loop, We hear maximum noise. There's nobody there. We do QRL a couple times, and then we can start running. We're not going to have to tune this loop again. The bandwidth is very small because this tune has very high Q, quality factor. It can be as low as 2.5 kilohertz. Usually it's more like 10. If it's not so good, it will be 30, 40, but then it starts losing a lot in efficiency. Another problem that you have is because the radiator is so small, but so small, your radiation resistance is in the milliohm range. It could be 50 milliohm, 500 milliohms. So any losses on the system, like the connectors in here, or ohmic losses in your variable capacitor, they all add up and make your magnetic loop be more and more inefficient. In fact, you can get as good as maybe efficiencies on the 70%, but if you go to another band where your radiator is too small, you can go down to the single-digit efficiency. It takes a very low footprint, but attracts curious visitors. Don't ask me how I know. I have been interrupted a couple times in the middle of a pileup from people that wanted to know what that contraption was. It does generate very high reactive near fields. The ARRL in the exposure calculator has actually a chapter on mag loops, and it will tell you how far you need to be from it. Even QRP powers generate very high reactive fields. The rule of thumb is that you have to stay away about 2 diameters from the antenna. It's not a big problem because when you're tuning it in receive mode. So except for the interaction of your body with the antenna, which is not so much if you are opposite to the antenna, then it's not a big problem. There's no exposure, and then you move back to your sitting position, your praying position, and you're far away enough. One nice thing of these loops is that they are very directive. The direction of propagation is within the plane of the loop, and they have a very strong null perpendicular to the loop. So if you have interference, like a neighbor or commercial towers when you're in a peak or in a POTA place, you can null a lot of that interference just by placing the plane of the loop against the offender. So that's very nice. And to finish it up, some very funny antennas. First, here's the KH1 again, and it has this funny little looking antenna. Is that really an antenna? It has 2 antennas here, right? Well, it's a plush toy, so it's not a conductive material. It's not going to be an antenna. It might be an animal antenna, but it's not really a radiating antenna. Well, how about the wet noodle? You probably have heard stories of people in the 70s when the propagation was so good that they said they work in the world with a wet noodle. In fact, there is a YouTube is going to show you what this guy has done with a wet noodle. He put a bunch of spaghetti inside a pot, filled it up with water, put a bunch of salt, let it soak up, took one of the spaghetti noodles out, put it on his tuner, put a counterpoise, touched the tuner button, got a 1-to-1, made a QSO. After that, he had a nice meal. He boiled the water and made spaghetti for himself. This other guy went to the beach. There's a lot of POTA beaches south of San Francisco, of course, next to the ocean, salt water. He goes there with his truck. He sets up on a picnic table just feet away from the water. And, oh boy, he forgot the antenna. So he goes back to the truck. He finds a long piece of tubing, transparent tubing that was sitting there in the bed of his truck. He goes to the beach, closes one end of this tubing, fills it up with salt water, puts it up on his on a pole, and finds a rusted nail in his truck, sticks it down from the tubing, connects the coax, counterpoise on the other side, punches the tuner, 1-to-1, makes a QSO. The same guy next weekend goes up in the mountains for camping. He's camping there all happily. I brought my rig. Oh, I forgot the antenna. Well, I still have the tubing from the beach, but I don't have any salt water here. So what can I do? Well, he sacrifices his dinner. He had a can of chicken soup, very, very high in sodium, fills up the tubing with chicken soup. You can see the yellow in his tubing, puts the nail back at the bottom of the tubing, connects the coax, counterpoise, punches the tune button, 1-to-1, makes a QSUM. Next weekend, he goes and flies to Iowa to visit his cousin. His cousin has a cornfield, and they're walking the cornfield, and he says, I brought my rig with me, but TSA took my antenna out. I don't have an antenna. His friend, his cousin says, no problem. You came at the right time. The field is mature. The corn is up high and is green and juicy as it can be. So they take one stalk of corn, they punch a nail at the bottom, counterpoise, tuner, punches the tune button, and makes a QSUM. Rudy Severance again. He studied, is it possible to load a redwood tree up in the Santa Cruz Mountains? So he experiments with loading it in the center, loading it at the bottom, put radials on it, and yep, sure enough, he can. And then since there's so many trees up in the Santa Cruz Mountains, can I find a tree that has another one that happens to be one wavelength, half a wavelength away, and now I can have two verticals in phase, and he runs all kinds of experiments, and eventually he had to stop because somebody started complaining. And finally, the famous or infamous light bulb antenna. This is not an LED, this has to be a filament light bulb. Many people in the past have used 100-watt light bulbs as dummy loads. Well, if you put a light bulb, is it going to propagate? Probably almost anything conductive propagates somehow, somewhere. So there's this club in the Pacific Northwest, and up until COVID, they were running one contest every year on how far can you get contacts with a light bulb antenna. And you can make your light bulb under certain rules. The feed line had to be a certain length, and in this case is vertical, bottom loaded with radials. And there is another one here that is 2 elements, top and bottom loaded. And if I remember well, the record has been about 400 and some miles. So yeah, anything can radiate. And finally, a conclusion. Anything conductive can radiate somehow, somewhere, and with some power. And here is another bearded ham doing POTA with some strange looking antennas. He seems to be happy. But the little girl knows better. You will have more fun if it's efficient and radiates to the directions of interest.